Hello, my name is Jason Rice. I am a web applications programmer, a bit burned out, so I moved on to C++, and now I'm actually doing web applications in C++. This talk is about using Docker to build C++ programs. It's a bit simplistic, and when I proposed this talk, I checked the beginner's box, maybe intermediate. So if you know Docker, this will be really simple for you. If you know C++ but don't know Docker, hopefully I can convince you to give it a try of using it to build your C++ programs. And if you know Docker but you don't know C++, maybe this is a good way to jump in. So yeah. So here is a recent XKCD comic about this guy that wanted to make this split-screen app on his tablet. And so he tried downloading the SDK and registering as a developer and getting the IDE. And then it turned out the best way to go about it was just taking two iPhones and gluing it together to get the same effect. So he didn't learn anything on how to write software, but he learned how to glue stuff together that he didn't understand. So C++ hasn't, we're only aspiring to reach this milestone of being able to glue things together as easily as some of the other existing ecosystems. And I've been around the web long enough to have seen different languages, before they had their package managers and then after, and it's hard to imagine what it was like, to go back and not have that tool. So I'm really looking forward to when C++ finally does, mature to this aspiration. All right, so in this talk, we'll be focusing on using Docker to set up a development environment to build targets in C++. We'll start out looking at Docker's images and containers, what's the difference and what do they do. Then we'll take a look at the Docker file, which is a DSL for making deterministic builds. And then we'll take a look at a very simple hello world example. And then we'll take a look at the multi-stage build process, which is a relatively new feature in Docker. And we'll take a look at building a tool chain or a compiler, specifically Clang and LLVM. And then we'll also take a look at how open source project maintainers can use this Docker to make it easier for contributors, so they don't have to have such a threshold for installing dependencies and whatnot. And it can be difficult on different platforms if you require like Linux-specific dependencies for building things like documentation and whatnot. So this can make it easier for people to do that. And then I also have this tool called cppdoc. It's experimental. It's just a Python script at this point, but it kind of provides an interface that makes it easy to do all these Docker commands. That has typical use cases that we would use for building C++ programs. Right? And I'm a little light on content, so feel free to ask questions or make comments. If you know or can make corrections, they're very welcome. And towards the end, I'll have a few live demos. And if we have a lot of time at the end, we'll do a live demo of compiling Meta Bench. And but that's just a joke. But yeah. So what is Docker? So Docker it's an open platform. It's actually a company. They have this open platform. It's open source. And what it does is it creates and runs containers, essentially. And these containers, typically they're Linux containers. And they can run in an isolated context that's separate from the rest of the host system, but it's not actually like a virtual machine where it has the overhead of having to run its own kernel and whatnot. And because of this, it has a faster startup time. than a typical VM. And it also has low execution overhead versus a virtual machine. And because of its DSL, their goal was to make reproducible builds. So it's like it should be, in theory, deterministic and pure, so that when you build something on 2 different computers, you should get the same result. Although, you know, it takes a bit of discipline to ensure that, because you're dealing typically with, you know, network downloading. You know, let's say you download a software package from GitHub, or you download a GitHub repo from the master branch. There could be changes on it that could break your build because you didn't anticipate the change. Another thing that Docker does is it has a registry that you can host images on, either locally on your box or remotely. And it's connectable, deployable, and it can even be used as a process manager. So Docker is actually used quite a bit for managing services. And instead of using like a native process manager, if let's say you built a web server or any kind of server for that matter, let's say it crashes, Docker can handle restarting that process for you, just like you would expect with like systemd or some native process manager. And it's actually pretty easy to use. So Docker images. So an image is basically just a file system. It has multiple layers on a union file system, and these images, each layer is actually immutable, and for like a given input, it'll have the same output, or it assumes that it'll always have the same output. So it creates a digest of every layer. So every layer is dependent on the previous layer, and it caches it using that digest. So when you build it again, it can just assume that it's using the same image, and just use that instead of having to do the expensive build operation. Yeah, so layers are built in a series. With the multi-stage build process, they're actually, you can build it independently, and then later a stage can copy files from that, from one or all of the other previous build stages, and then they will become dependent on whatever they copy from those other build stages. So the files system, it uses a copy on write strategy. So in a subsequent build stage, if you modify a file, that's when it would get copied over, and not until then. So it's actually pretty light. So each layer only has differences in the file system. So if you just change one file, the only overhead of that would be the size of that file. And Docker images are created using the command line tool, Docker build. So any questions so far?
So they start off as little tiny things, and you add sequential build steps that populate almost like a file system, snapshot, file system, snapshot, file system. So if you're going through the steps again, it just kind of grabs it from the middle.
So the question is does it, I'm sorry, what do you mean by grab it from the middle?
So if I had like a build sequence that the first 4 steps are the same, but the 8th step following are different, and it goes off of a previous build,
all right,
can it just kind of assume that the first couple of steps are there, I'm going to use it from the middle?
Yeah, so the question is, can it, if you make a change to one stage that's in the middle, would it like invalidate the cache for the rest of the stages? It would. I have a diagram that explains that a little more simple. But yes, so another thing about the cache is that, so it has this digest. If you make a change to the input, the digest would change, so it wouldn't use those cached values anymore, but it isn't necessarily invalidated, because if you changed it back, it would still find it in the cache. So the one problem with that is you can get a buildup of dangling images. And they have like a Docker prune tool that can help remove those for you. How many people have used Docker? How many people have used Docker to build C++ programs? It's quite a bit. All right, so this is a diagram of the cache invalidation. So you have these layers, layer 1, layer 2, layer 3. And if you made a change to layer 2, just like was in the comment, it would invalidate every layer after that. So it would have to build. So you can be strategic with how you build your layers. Like if one has an expensive download, you'd want to make it in a separate layer. And if the order didn't matter to you, you'd want to put it in one of the higher layers so that if something gets changed a lot, it wouldn't invalidate the layer that has the expensive operation. So it's a sequence. So containers. Containers are like, they're a runnable instance of an image, and basically it just adds a final immutable layer. So when you run a container, you start out with the image that you're running, and then you can make changes to it, you can stop it, you can restart it, make more changes, and that's basically, it's kind of like an image, but they call it a container because it's mutable. The overhead is pretty low. It uses the copy and write strategy, and I believe the overhead is around 32K for a file system. You can create mount points on the host file system. So let's say you're compiling a program and you wanted to be able to have the source code persist on your host server. You can let's say you mount like /opt/source to like the current working directory is what I use in some of the examples. And then they have Docker Compose to make these containers composable, and it's kind of like Odin's mix-in pattern, in that you can actually just have these mix-ins and you provide access control to different functions. But in this case, you're providing access to different network ports and different like bind mounts or volumes, which are basically file systems that would persist on the host. And you can even export these containers to a raw file system or run it as a standalone virtual machine that doesn't even require Docker. And in the references at the end, I have a link to a blog post that demonstrates how they do this. And to run a container, you use Docker run. So building images is Docker build, and then running containers is Docker run. Right. And this is a diagram of a container. So you have your host system, and then a container, and you can see that there's a bind mount, which is actually, it's also called a volume, but they prefer the term bind mount because a volume is also something that a service would own. And it doesn't necessarily have, it's kind of like an anonymous mount on the file system that Docker manages. And it makes it easier to migrate and back up. But in this case, a bind mount is, you're mounting it to a specific named location on your host, which is what we'll be doing, because we're not doing services, we're building applications. And then you can also expose ports to the host system.
You say expose ports to the host system. Do I have to explicitly expose ports to the outside world as well, or are they implicitly always available?
So what do you mean by outside world?
Like, I don't want to connect to a service on the host. I want to connect to something on the internet.
All right. So the question is, when you explicitly expose a port, does it necessarily expose it to the outside world, as in the internet or the network? It really only exposes it to the host system. So if it would be exposed to your network if you didn't have some kind of firewall set up. So yes, when you run a container that, let's say it has port 80 exposed, and you tried to run another container that tried to access the same port, it would fail because the port's already taken up. So it uses a port on your host, just as like a web server would. So you can use it to expose it to the internet. But yeah, it depends on your system's firewall. All right, the Docker file. So the cool thing about Docker file is it's documentative. It's a DSL, and it defines steps to build an image. And each directive defines a layer. So you start out with a base layer using from, and then it defines layers that can copy files into the image being built, or you can run a shell command using run in the image's context. You can also use it to specify default environment variables that will be available in any container that is run, but it has to be in that build stage. And you can specify volumes, but the only time you really specify a volume in the Docker file is if you're running a service. So let's say you want to run some server that has a log, and you don't really care where it is on the file system. It's just you want Docker to manage it for you. Then you would use volume inside Docker file. Otherwise, we express bind mounts as volumes at the command line in our use case. Yes. Oh, and you can also pass in arguments from the shell. So this is a C++ program. In case you guys aren't familiar, all we're doing is printing out hello world. I'm pretty sure a lot of people maybe started out with this. So like I said, this would be pretty simplistic. And so the file layout of our example, and you can find this on GitHub under my repo, and I have a link to it at the end. So the hello world example has a Docker file and main.cpp, and that's it. And this is a Docker file. It's really simple. I'm reusing one of my CPP doc, base platform images. And what I do is I call the copy command, which takes a file from. So when you call docker build, everything in the current directory gets copied into what they call a build context. And all the files in that build context are available to be copied from the host into your image. So in this case, we're putting the main.cpp file into a directory called opt/build. And then for convenience, we just use the work dir, which sets the current working directory for subsequent shell commands. And then in the run, we run a shell command. And we just run clang with libc++ and libc++ ABI because the base image, that's all it has. It doesn't have libstdc++. So if you don't specify it, it won't find IOStream. And then this command directive at the bottom. So what that does is when you run the container, this isn't part of the build process, but when you run the container, this is what gets run. So we're actually just executing. So when we run it, we execute the program that we compiled.
So when you run it, it doesn't run, it runs command, or it builds and it runs run.
So when you build, it does everything except command, and when you run, it runs command. And the way it works, they actually have two directives. One's called entry point, and another one's called command, and they have a lot of different ways to use it. That's kind of complex, and I won't try to explain it too much, but the idea is, in this case, we have like this JSON array, and it will run this as a standalone process. It won't even run it in a shell. But if we just had, without the array brackets and the quotes, if we just had A out, it would actually run it in a shell with the environment variables and everything. And the reason for the difference is that Docker is often used for running services where you don't really want the overhead of having a shell, and it was originally meant to just run a single process, but then they later added the ability to run it in a shell, which is actually really, really useful to us who want to do stuff like build C++ programs. And in fact, Docker is built in a Docker context. So here's the terminal output. So we call Docker build up here at the top. And I give it the option T, which is a tag. It's just the name of the image, which I can later use to run it. It can also be anonymous. I don't have a lot of use cases for making anonymous images like that, but it does later give you the name of it. So maybe if you're doing this programmatically, you could just get the hash value from the output. So you wouldn't have to create a name. And then we have an image called hello world. And then we can run it. Docker run hello world. We run the image as a container, and it just prints out hello world. So does everybody understand the process? Like I said, if you know Docker, this is really, really simple.
Question, does it actually exit afterwards, or does it leave me in the shell of it?
So in this case, there is no shell. But even if there was, once it terminates, I do believe that it would exit the shell. But there are cases like where you can run a shell where you wouldn't be able to get out of it. Actually, I'm not sure about that, if it exits the shell or not.
There's a command line option. I think it's -I for
Yes.
interactive, and then it doesn't exit the shell.
Oh, right. Okay, so I'm sorry, the question was, would it terminate immediately, or would it hang around until like you somehow canceled it with Control-C or something like that? In this case, it would terminate because there is no shell. And the comment was you can, if you were running in a shell, use the I option for interactive mode and I think there's a T option as well for keeping it. Wait, does that enable it to quit the shell?
I usually use -IT, but I forgot what the T stands for, so.
I think it's terminal, like TTY. So you would want to use that if you were like in a bash terminal or something. You were next.
Yeah, so if you go back by one, just so I can grok this, or one more. So the idea being is you build it, runs all the commands that you have for there, and it has a command. Now, does it actually run a.out, or is it one of those? No, it's all prepped and ready to go. You've got this Docker image that when you run it will actually start executing the run command.
All right, so when you run build, it just runs the build steps and not command. So you can see step 1 through 5. It says running. I don't see that. It doesn't actually run the a.out during the build stage.
So it sort of just like preps it ready to go?
Yes. So, okay, I'll repeat the question. The question was, does it just prep it ready to go and run the a.out command? It does not run the a.out command until you run the container.
Is it storing the a.out file then?
Yes.
File system?
Yes. So you're building a file system, and the steps are, we add main CPP, and then we compile. So the result is really only 2 differences, and they're separate layers. The copy one being the main CPP, and then, like, I guess the 4th step would be adding the a.out, and that would be in you would just have this file system with those, and then when you run the container, it runs that file in the file system. Yes.
Just want to add something. So if I remember correctly, command CMD, right, is optional. It's not required. It's just the default thing that is going to be run when you actually run your image after building it. And well, you build it, and then when you run it, it's like the default thing, because you can also provide a command to run when you say Docker run. So you can say Docker run this image, and by the way, execute that thing. That should be the command that you're going to execute. And so what people do sometimes is, what I've seen done anyway, is they're going to actually provide the image, and then as the command that they're going to run when they run the Docker image is just bash. So what happens is you just get dropped into a shell, which is on that file system, and then you can use, basically if you built your library or if you built compilers and stuff, then you're free to just issue whatever commands you put in. So just some additional information.
All right, so the statement was that the command directive is actually optional, and I believe you said that the default is bash, right?
I don't remember what the default is.
Oh, I think it is bash.
Okay.
So it'll run bash by default if you run, and you have to give it IT, obviously, to run a container. And also, like, if you were to create an image that had this as a base image, this command would actually just be ignored. I'm pretty sure.
The terminology is really confusing.
I'm sorry, the terminal output?
The terminology is very confusing. But like the fact that they use this command to really say like,
Yeah, it was originally meant to, like, this is what happens when you run the service. But yeah, yes?
Does it automatically take all the output from the Clang stage there and put it into the file system?
Yes.
Or is the command necessary to copy a.out into that file system?
So the question was, does the run take all the files that output from Clang and put it in the file system? Was that correct?
Yeah.
Yes, it does.
Okay.
So I'm not explicitly putting A out anywhere. It just happens to be inside opt build. The Clang process would create that artifact, and it's just on the file system.
Whatever the actual build command produces will be part of the image.
Yeah. So anything that's created in the build stage or the shell command just ends up on the file system. That's it. Yes.
I mean, effectively, it's just spinning up the Docker image and running that command in the work directory, and the results is that the out is in that work directory, right?
Exactly. Yes. So if I didn't specify work directory, yes, it would not even find A out. Well, it would find it because it's still in the same directory as the shell command. So it would just be whatever the default working directory is. I just happen to specify opt build. It's probably not even necessary in this case, except that I copied main into opt build, I guess. All right.
What happens if the compilation fails?
The compilation fails. So if the compilation fails, so any of the directives exit 0, it will the whole build will fail pretty much. So like also if you give the build command the RM option, it'll remove failed build images. And if you don't, it'll just, it'll stop, and then you can actually go and mount the image to see what went wrong.
Do you mean that it's non-zero for error?
The process exit code?
You said if...
Oh yeah. Yeah, I'm sorry. Let's just say if the compiler fails.
That also then depends on whatever you're running as a build process to give the proper error code. Otherwise, it doesn't know what to do.
Right. So I'm assuming that exit 0 is the only acceptable outcome to say that it's a successful build.
It's kind of important because if you're your own build tools and you define something else as exit code, then you're
Right.
screwed with this.
But don't do that.
All right. So we only got 15 minutes left, so plenty of more content to go. So all right. So we did this. All right. So this is the multi-stage build example. Here's another simplistic C++ program to try to convince you to get on the Docker C++ train if you aren't already. And in this case, I have a CMake file, and it's really simple. With the add definitions, I know that's not the best practice, but I have not gotten the proper way to work yet. But I know with 1Z it wouldn't work, and even with 11 I can't seem to get it to work. But one thing worth noting is that the targets, it installs it to the bin directory of whatever the prefix, installation prefix /bin. All right, so here's the Docker file. I'm sure this might be difficult to read, but just notice that I started indenting each of the directives that are contained within a build stage, and the build stages are separated by the from directory, from directive. So anytime you say from, you're starting a new build stage, and you can give it a name. So in this case, I'm starting with my cpp.doc base image and calling it as Linux, so I can use that later to copy any artifacts from this build into the next one. And I can leave other artifacts behind, like if I installed a compiler or something like that, I wouldn't want that shipped with my binary. And in this case, I'm still copying main, copy CMake, and I do the typical CMake build, but also I'm specifying a tool chain, so my base platform image has its own CMake toolchain, which is really convenient because I know the system has a specific compiler, a specific setup, and I can make a lot of assumptions in the CMake toolchain, which can bypass a lot of checks and make it a lot faster to start up. And then I set the prefix to opt install, so if I'm doing something like cross-compiling, it doesn't accidentally get into user local where it's mixed in with like maybe system built dependencies. And then I build train and I install it. And I do the same exact thing for my Emscripten build. So my build stage has the alias Node.js, and it's exactly the same. So I'm building for multiple platforms. I don't normally do this way in multiple stages. I just wanted to demonstrate the multi-stage process. And we're just building for different platforms. And for here, we're copying from Linux and then from Node.js. That's how you copy from a previous build stage, using that from notation. And we're just copying from that stage's opt install to this stage's opt install. So does that make sense to everyone? And then in my command here, I just copy the files to a directory called opt target, which I'll mount to my file system on the host. So this is the command to build. I'll spare you the output. And when I run it, so this V option, it's called volume, but really it's called, in this case, it's a bind mount because we're binding it to a specific location in our file system. And I just put it in our current working directory /target, which is where I want to put my, built binaries in JavaScript. And I wanted to do an OS X build, but I didn't have time to get it set up. So I could run it in this Mac as a demo, but here's the bind mount parameters. And then when I run it, nothing, you don't get any outputs because it's just copied files. But now I can run Node.js to run my built JavaScript file from C++, and prints out the Docker C++ train. So does everybody understand the multi-stage build process? All right. So building a tool chain. So there's some advantages to using Docker for building a compiler. One reason is before I started using Docker, I was typically going to some blog post that I remembered. Like every time I moved to a new desktop or whatever, I'd have to reinstall whatever compiler I wanted to use or whatever. Or you can also have a bash script, which would be just as effective, but one major difference is that the bash script can't make assumptions that it has complete control over the file system. So you couldn't have it install the dependencies that you would need to build this compiler. And additionally, maybe the dependencies to build it could be discarded so that then you install just the resulting binaries or whatever is necessary for actually using the compiler. And that's much smaller. So this is probably difficult to read. In this case, I'm just going from a base OS layer called Ubuntu, the Bionic version. I call it fastcomp build. And this arg argument sets up a argument that can be overridden at the command line. And then I also have to specify it in the build stage, otherwise the build stage won't know about it. So this is a tag off of their GitHub repo. And fastcomp, if you don't already know, is the LLVM fork for Emscripten. It's called the Emscripten fastcomp. So here's where we install our dependencies. So I have a little inefficiency here. So I have curl and tar, and I just use that to download Node.js, which I should have done in a separate stage, but I'm not doing that here. I could have saved like probably a little bit, a couple megabytes at least. All right. And here I use git clone. Unfortunately, you can't clone by a revision like it's the git SHA, so you have to use a tag. So here I have the convenience of using git clone with a depth of 1, so it doesn't download the whole history. And so So I download mscript and fastcomp, and then they also have a fork of Clang. I download that, and then the libc++ and libc++ ABI, because I'm actually building the backends for both the JavaScript backend and x86 and ARM, just for convenience. And then I run CMake for building LLVM as release to the user local prefix, and I specify my backends that I want, and turn off examples and tests because that's really expensive. And if I ran on J4 on this computer, it'd probably melt it. And then when it's all said and done, this is almost like synchronization if you think about it. I just copy all the files from each of the build stages and leave the rest behind. So in fact, no, I guess I don't have, this isn't the example that has the inefficiency of keeping curl and stuff installed. So here's the mscript and SDK itself. I put it in a separate image so I can use the fastcomp for x86 builds too. That's about 300 megabytes, LLVM and Clang. And then this adds a significant amount, a couple hundred megabytes, I think. So it has the same, it actually derives from the compiler I just built. And then, and then it depends on all these for running Python. The Java runtime, I'm not sure why that's needed. And here's where I have the inefficiency with curl, tar, and XZU tools, because I actually, later I'll install Node.js, which I could have done this in a separate build stage. But you need Node.js for running mscripting. And it's also useful for testing. And here we just clone the repo, and that's it. And I delete the tests because the tests are huge. How much time we get?
5 minutes.
Okay, we got 5 minutes left. I might skip some stuff. Oh, I know, I'm not going to skip this. All right, so let's say you run an open source project and you want people to contribute, but it's a high threshold for entry when you have to install a bunch of files. I like contributing to HANA. It's probably my favorite open source library. And it's got cutting edge CMake. And I don't update my Ubuntu often enough to keep up with that. So like I had a problem where my CMake was like 3.6 or something, and HANA required 3.9. So I just did it inside a Docker container. Also, it has to install Doxygen. In this example, I omitted Ruby for building the benchmarks and stuff because I actually wanted to do this as a live demo, and that would take a long time. For some reason, installing the gem files is really, really slow, like minutes long. I have no idea why. So the comment was he wants to get rid of the benchmark stuff. And then I also installed Node.js because I was lazy, and I used the HTTP server just to have a quick and handy way of serving the files. And I'm going to skip this. I'm going to do a live demo real fast. Oops. All right, so we got HANA. And I forked this and I added 2 files. I added a Docker file, which is really simple. I just install GCC, Doxygen, Valgrind. I guess I already showed this to you. And then just for convenience, I added a make file that has the Docker commands. So this is tedious to type in every time. As useful as Docker is, I think the command line can be a little tedious sometimes when you do the same thing. And so I'll build the image by calling make image. And it was already in my cache, so it was pretty fast. So I have to copy the files over to create a SHA to see if anything changed, because it's copying files over. But just to look at that make file real fast again. Note, when I run it, I'm binding port 8080 here. And then I also mount opt source, so I don't have to copy that into my image. And it's read only, so I don't like accidentally modify source files when I'm building. And then so I make dev, I think is what I call it. So running it, I don't know if I'll stick around. It doesn't find Ruby. It finds Doxygen. The CMake is pretty.
3,000 tests, that's why.
Yeah, lots of tests. So we can come back to this. It doesn't take. What? Yep, wasn't done. All right, so I'm going to make doc. All right, so the next, we'll come back to that in a sec. The next thing I wanted to talk about, I only got a couple minutes, I think. CPP.doc, it's just a Python script. What it does is it manages dependencies. And like I said, these are supposed to be, in theory, deterministic builds, but in practice, it is possible to make a build that isn't deterministic. Like, let's say, you download files from some source that could change, like a master branch. What CPP.doc does is it actually looks at GitHub, or it uses Git to find the SHA of the branch, and then it locks it in, kind of like I don't make a separate lock file right now. I do want to move to that, but right now it'll add into the configuration file the revision and lock it in place. So it always uses that. And the cool thing about that is, like, if you want to upgrade, then you don't have to clear your cache because it thinks it hasn't changed. So here's like a sample of I used to have any files. If you look at the README, it's a little simpler, but this has the ability to have more features. So I moved to JSON config. So I have these, my project name is Nibdal. I have a platform I call Develop, and then the type is Linux x64, so that looks for my Docker platform image, although you can override that with your own platform images if you want. And then I have deps, and each dep is an array because you can have multiple deps installed to a single build stage, because some deps depend on others, and it's all flat, so you have to define every dependency. So there's no like recursive dependencies. Although I did add another type of dependency. So this one, by default, it looks at GitHub for the repo, like in this case, boost or callable traits. But you can also specify the type of dependency. And the only other type I have right now is you can actually just specify a Docker image. And eventually I want to add like Conan and maybe a VC package or whatever. See if that, I haven't seen if that's feasible yet. So doc was made. HTTP server. And then, so now it's running. It's still in the terminal, but it's running an HTTP server. And I just made a small change to the documentation. It's boost, huh?
Do you notice that other thing is up in your web browser? Can you talk about that?
Oh, yeah. So, yeah, I had this open. So the boost repo on GitHub got a commit. I guess this was 9 days ago, but I just saw this on the mailing list.
It hasn't been committed yet, but yeah.
Yeah, I think this PR is a work in progress. But they're trying to Dockerify Boost, and or at least make it buildable with Docker.
Make it so that you can make a Docker container that contains all of those.
Yes, and that would be very useful. So if you get a chance, check this out on GitHub and give it a little thumbs up. So do we have time for another quick demo, or are we out of time now? All right, so we got a little more time. I'll just skip my slides on the, oops. Exit. All right, so in Nibdal, I have a cpp.json file right there. And if I have that, I can run cpp.doc dot, not dot, but init, and that's what locks my revisions. But since it's already locked, it doesn't even have to look because everything already is locked in place. And then I can do cpp.doc build, which builds an image with all the dependencies. My platform name is develop. So it's going to build an image with all my dependencies. It's really fast because it's already built. And then I run, for that, I run dev, cpp.dev. Oh, you can't even see it. cpp.dev develop. And it just instantly creates a shell with which I can start running targets. So I can run make run, and sorry, you guys can't see that. Make run example pipes, and it compiles the pipes example, which on this computer, I guess maybe because it's a smaller computer than my desktop and it's running in a VM because it's a Mac, it compiles a little bit slow. So that's it. So that's one way you can use a convenient way of managing non-trivial dependencies. So thank you for coming down. I appreciate your time. And I'll skip that stuff since we're out of time. All right, thank you.